it's really great to have literature and the community around it of well-understood tools and ways of thinking about how the protocol operates. Has been very practical to implement. One of those sort of tools that you get here is like this little tool here, which builds a which can give you an animation of how the protocol works. So it's showing all the members of the cluster, how messages are flowing between those members, and ultimately appending entries into a log and agreeing on the same entries across the whole log. So that's Raft. It's a well published protocol. We need to use it inside Neo4j, inside the database. And how do we do that? Well, we've got a picture to explain. It's a little bit complicated, but I'll go slowly. Try to get through this. So we're going to start on the left, and we've got data coming in that we want to commit in Neo4j. So each of these coloured squares is a transaction that potentially might get committed. And the part on the left, where it says Neo4j Raft implementation, that's the part that is, we use Raft, the Raft protocol, to manage that part of the system. And the way we think about it is that we've got a consensus log where incoming transactions off the network, we append them to this transaction log. And you can see that on each of the servers, each of these rows, a different server. The log is slightly different lengths on some of these servers. But what's really interesting is that from our perspective, compared to what we do on our own database, is that we actually write this stuff to we durably store stuff before it's actually committed. So as Max was showing earlier, like we write it straight away before we send it even to the other servers. But that means that potentially it might not get committed. It's actually possible a transaction can end up being rolled back if the protocol works out that way. So that means that the right-hand side of this log, the bottom three rows that I've outlined in blue, those can actually, that's got some examples in there of transactions that are different between the logs. So we've actually got divergence in the consensus log. However, the protocol means that we can, in the end, we get to a consistent set of entries. And each of the individual servers observing that log can determine when it's safe to consider an entry in the log. So each of these cluster members can, individually observing its own copy, its own version of the consensus log, can determine that an entry is now safe to be committed through the protocol. And once it determines that, we can then move to the right-hand side of the diagram, where we have transaction logs, sequence of transactions on each of the servers. And you can see that those logs in this example, they're slightly different lengths. Transaction 11, if you can see the numbers, only exists on 2 of the 3 servers at this point. However, they're all consistent, prefix consistent. If you go from the beginning of the log up to a point across them, they're also you can't look in a position and find 2 entries of a different cluster. And this is great because what we're using the protocol consensus for exactly what it's for. It's for agreeing an ordered sequence of values, and we just rely across the whole cluster that to work out, give us transactions that exist across the whole cluster. And ultimately, what we do is create a graph. That's the whole point. So on the right-hand side, we've got little representations in small graphs, and I've color-coded the nodes so that that transaction 11, the green one, is creating a green node that's dependent on 2 of those 5 servers. So that's the process. That's where we fit Raft into this stuff.
Yeah, so that's how the core servers work. But as you know, there's a whole other side of this, is that there are the edge servers. Yes, those core are small, so the edge servers are an entirely different piece. They're completely different. They don't partake in this perform mid-process. They don't. They have a wholly different responsibility. They don't save the data, but what they do is they sort the data in a way that allows for an incredibly massive amount of throughput. So you can scale these up in a way that you don't have to worry about them, being lost later on. So you can auto-scale them in a way that you can then throw them away later on when the load goes down and you don't need so many servers. And they're basically responsible for increasing read throughput. And so how do they interact with the rest of the cluster? So as you know, the core servers are the ones that take in the writes. And so that interaction, as you know, it's a write that goes to the core servers, and they get propagated to all of those. Later on, when they've committed it, when it's been replicated, of course the end-user application will be told about that. But then downstream of that, the core servers are pushing these updates to the edge servers, so that they also become updated as soon as the write gets applied to the core servers. And so that when you're going to do reads, you can then load balance the load across all these different read servers. So when you do a read, it'll be successful that those updates have been applied to the edge servers based on information that they got from the core servers. So it's a much simpler process, but it really allows you to scale these out to massive amounts. So this is the thousands of servers claim that Emil was talking about.
So I think probably best to, I'm going to save the questions to the end. I think we've got quite a lot to get through, so I'm going to try and keep going. The real question is, we've added all these read servers, and it's kind of, why does that help? Like, why is that a good thing to do, to have lots of read servers? Surely we need lots and lots of write servers as well to make this useful. Well, the reason why it is helpful in a graph application is we've looked at what our users do. And I've got this picture to try and explain what we see our users doing. We've got the same graph on the left and the right hand side of the slide. On the left hand side, we're showing, imagine some part of the graph being updated. And when it gets updated, we're highlighting it in blue. So you can see like individual relationships getting updated. On the right hand side, we're showing queries that might be running. And those queries are traversing an area of the graph. So they're exploring out from a central point and it's exploring a neighborhood around the starting node. This is kind of typical of what we see at a very simplistic level. It's typical of the kind of things that we actually see people do here today. The simple way to look at it is if I just count what's happening, the transactions on the left-hand side are very small. The updates, they're a small number of nodes and relationships. So here it's just one. It could be 10 or at most like 100 entities. Whereas on the read side, we're talking, it's really common to be traversing thousands of relationships. It's like the absolute normal kind of thing to be able to compute a recommendation or to find a path. You actually explore much larger amounts of the graph. So this is really a property of the graph model. It's because it's a really normalized way of storing the data. It means that when you update something, it's not the same, it's not the whole value you're going to read back later. It's a component that's going to influence a much larger query. So the things on the right, those are hungry for CPU and memory bandwidth. So that's exactly the area that we want to scale out, and we can do that. We don't really have an enormous amount of load to do on the right side to still benefit from an enormous number of recommendations or analytics queries that can happen over a much larger cluster of high CPU servers. So that's our kind of insight driving this architecture. It's a particular style of what people do with graphs. So
so we've basically covered the main architecture of how this works. So there are two different parts of the cluster, the core and the edge. And And we see that they're architected very differently. Small servers with small amount of servers to the core and main servers to the edge. So,
with the AV situation, this could be a challenge. So let's see what happens.
So we're going to try to do a small demo. Unfortunately, with things like distributed systems, demos aren't that interesting as long as everything's working. You can't really see anything exciting happening. It's more fun when everything's on fire, but we're not going to do that today. Yeah, that'd be really awesome.
So I'm just going to put some time to scale this now. Okay, so still there? Still okay. Cool. So I'm just going to log into this. So if you want to you tell what to do and I'll try. Be very careful. Okay. So we start the cluster here, and we at the moment this Neo4j browser view is pointing to one server in the cluster. You can see from the address we're running in EC2. And the first thing I can do that I really want to kind of show that we're. Okay, so. Can people read that? Is that readable? Yeah, I can do that. I need to try this. Well, if you're doing a presentation on Neo4j, that's supposed to be helpful for kind of when your projection's a bit kind of fading to put bigger lines around things and make things black. Okay, so I want to show that the servers are that the cluster is kind of self-aware. So self-aware is aware of its is aware of the structure. So one thing we just built in here is into the normal sysinfo, which you might use to look at the status of a Neo4j database. And there's a section added in here which just lists all of the servers that form the cluster. And it's actually a nice kind of, not zoomed in too much for the CSS, but there's a nice interface here, so I can actually just click this open link, and it opens a new tab which allows me to run a query on that specific server. So I've got some awareness of what's going on in the cluster. What I can also do is, do a lot of this stuff through procedures. So I can run a procedure that does something very similar. What should I do? I'm going to do a picture. I'm going to go straight to that. So this is something that Max, you want to talk about? Yeah.
So we have the sysinfo information there that shows you all the information about all the servers in the cluster, which is useful to have in the browser for debugging, making sure as an administrator that the cluster is set up the way you want. Everything's working fine, and you have the nice open button so you can log on to another server and try some queries there and make some sure it's correctly. I wrote this nice procedure this morning to try to visualize this a bit better because obviously CSS is not great, so being able to visualize things with nodes and edges is way more better. My grammar is also way more better. So this is a procedure that you can run that also gives you the same information but in the Neo4j style graphical format. So you can see when you run that, it gives you an overview of the current cluster configuration. And we have the core nodes in the blue, and the way they align that the leader and followers is implementation detail, but that's one thing about how they work. And you have all these read replicas that are strong. So those where you're going to be able to scale out your read queries to get massive throughput. You can see that the read replicas are a much greater portion of the overall cluster.
We intend to demo it by running a really large cluster.
You can run a really large cluster, but there's a short warning. So this is limited in use, but it looks really cool. You can see that we actually got a cluster running and a few things on it. So that's a procedure that I wrote, that it'll probably be an APOC sometimes. So there's another procedure that's actually built into the database, so when you download the data, you can actually use this one. It's a cluster overview. So that gives you the same information basically as the sysinfo.
So it allows you to programmatically inspect the state of the cluster, which is useful from within the cluster to be able to work out what's going on. Cool. So, how do you actually write an application to use this clustering architecture? The first thing is, Emma also talked about this morning. Back in Neo4j's 3.0, we introduced this new set of officially supported language drivers. And this is a kind of a diagram to show the architecture of that overall. We would expect you to write if you want to write a graph-based application, you can do it in lots of different ways, lots of different architectures you can use. But the one that we're kind of pushing towards is this one where you write your application in a general purpose programming language of your choice, so Java or C# or Python or Ruby, and with that you use a driver written in the same language that you're writing your program in. So it's got the same idioms and the same same ecosystem around you as your application. And those drivers that we released in 3.0, they use this native binary protocol to talk to an interface server. So that's what we're showing right next. Those drivers are available in the supported language at the moment. There are some other community supported languages that use the same protocol. And there's a whole load of stuff online about how to use those drivers. We try to make them consistent as possible across the different languages while still being idiomatic in those individual platforms. Right, so this is what it looks like. If you're going to use a driver, we introduced a URI scheme called Bolt, and to connect to a database, you use a URI that looks like this. It's got Bolt : and then the address of your server. That's the code you use. How we've done clustering is we introduced another URI scheme. So we've added in this plus routing part. So now it's still Bolt, but it's Bolt plus routing. And this gives you another layer that insets between your driver and the specific server and does the routing, figure out where to actually send the requests. And the reason why we've gone down this route is we want it to be really easy to transition from writing an application in test, where you might have a database running on your laptop or you're spinning up in a test, and you just have a single server in your the connection string. Take that same application code and go straight away and run it in a cluster. All you have to do is swap in a different connection string, a different URI, and you get to the running clustered mode with the load balancing. That's what it's designed. I just wanted to point out is that this server that we at the moment the current API is a server, and it's a server that we use to bootstrap the whole process. So it's something that has to be available just at the time when you start your application up, and then it will learn the membership of the cluster, and as it changes over time, as you replace servers, as you expand and contract the cluster, it will learn about those members over time through the discovery protocols. So this is what ends up happening when you use this. So we've got on the left we've got some popular mobile devices representing being used by ultimate users. Their names up there, and their request when they press a button on their phone, it gets routed ultimately to an application server somewhere. So we've got a number of different application servers, and it's going to any of those. And then in turn, from those application servers, within the driver, there's routing going on. So you end up on one of the many servers in the cluster. And this is how you do it. But at the moment, we're showing the Java code. Obviously, there's equivalent code available for all the other languages. But this is how you would tell it what routing to do. So the key point on here is that up in yellow at the top, we've shown the bulk plus routing URI scheme. So that's where we tell it to do the routing. And then we need to ask the driver. This is basically the same pattern as we had for 3.0. We need to ask the driver for a session, and that's our kind of lease on a use of a server. And we say, yeah, we want to use this for write, so you better send it to a server in the cluster that's going to support write for me. And so that's the semantics there. We pass in access mode write. Then we begin a transaction as usual, commit the transaction, and it will magically find its way to a server that's currently suitable for writing. What's on the right, we want it to read, and you can imagine it's just the same, but we specify the read access mode, and then we're going to go to a server that's suitable for reading. So that's quite likely to be a server in the edge.
Right. So that's how you use the driver, and that's how it lets you interact with the cluster. But there's one aspect of this clustering story that still needs to be told, and that's consistency. So consistency is something that is a really nasty thing if you get it wrong. So.
We looked at pictures a bit like this before. Now we're looking at the stream of transactions applied on each of the server in a cluster. This is this situation where you can see transaction number 11 is only applied on 2 out of the 5 servers. You're always going to have this situation in a cluster database. If you required all of the servers to update lockstep before you consider anything committed, it would be very difficult to scale beyond just a very small number of machines. Because if anything goes wrong at all in those machines, you can't do any work. You can't move forward, and you're slowed down to the speed of the absolute slowest machine within the cluster. So you would expect some amount of lag between the very fastest and the very slowest server, and that might be under a millisecond, or it might be, if something goes wrong, if there's a network partition, it could be seconds that they're behind. Anyway, the point is that you've got to be aware that this could happen in any situation where you've got multiple servers and you're sending load to different ones. You could see different stuff happening. So on the top row, if I run a query on the first server, I'm going to see transaction 11, and then a little bit later, I do a similar query, and oh dear, it hasn't got transaction 11 yet. So it looks like I've kind of gone back in time. I've kind of lost the thing that I'd seen previously. And that's why you need to be aware of it. Maybe it's not a problem. Maybe we can deal with it. And I think, going back to my pretty slide here, I think maybe this is actually fine if you're doing analytic queries and you're trying to make product recommendations based on what other customers have bought, all other customers have bought recently. Does it really matter that you've got absolutely the last transaction every time? Well, in fact, you can't, because they're always coming in. There's no connection between you and the other customers. So actually, what you have is always a bit out of date. So actually, sometimes the consistency just doesn't matter. But there are situations where it does matter. So Max has got an example.
Yeah. So there are some situations where this can be extremely bad for the user and it's a terrible user experience. So we've got one example here just to illustrate why this would be a bad thing. So say you've got you're running a web store and your customer needs to log in or create an account before they can do the purchase. Okay, so I'm a new user, so I need to create an account. So I try to do that. I make my credentials, create my account. So it's doing it right somewhere. I don't know. So I go back to do the login. Now I'm going to log in because it's not a great website that just logs me in automatically or something when I create the account. So I'm going to log in and I try to put my credentials in. I'm going to hit login. Oh, what happens? The account's not found. Like, that's really jarring. I thought I just created an account. Did I just forget what happens? Well,
does anyone ever see these kind of glitches? It's kind of like
it's
glitches
sort of
in the network. Yeah, it happens, right?
Yeah, because a few seconds later, I'll just keep hitting the login button because I'm not crazy. I know I just created the account, and eventually it'll work. so this is a really common problem. I'm sure if you haven't seen this problem, you've probably seen something where you change your profile photo on some website. You upload a new picture. Oh, that looks great. I'm going to save that one. Then I go back to the home page and it's still the old ugly photo, and that's not updated. And if I wait a few seconds to keep refreshing, eventually, that great shot's there. And this is really annoying for users. And so why do we have this? It doesn't work because these systems are implementing something called eventual consistency. So it's a different level of consistency, much lower. And basically it means that the system will be consistent. When it's consistent, well, that's anyone's guess. It depends on the weather. It depends on how far away the servers are. It's really anyone's guess. So there's no strong guarantees about what's going to happen. And you're going to have these experiences for the user where they try to do something. They have to keep refreshing and wait a bit and see the changes propagated. And so if we try to pull back the veil and see why this happens and try to illustrate it more deeply, what happens is that when the user does something, creating an account, so it's writing some data to the application server, which then forwards that to the database. And that database then commits it by adding it to its log there on the end, and applies it to the data source, so the graph in this case. That happens. Now so there's no consensus going on. There's no quorum rights or anything. It just goes straight back to the end user. Great, we saved it. It's saved somewhere. Carry on. The user then tries to log in, put their login details in. The cluster is replicating these transactions eventually, so they get updated somewhere else. So you can see the rest of the members of this cluster. They don't have 11 yet, the red one, but they just got the yellow one, and this guy on the end is a bit slower, so he hasn't got any of that yet. He's just stuck at the teal color. Time goes on, the user hits login, he gets routed by the application server to this database cluster member on the end, who doesn't have that update to the database yet, so he doesn't have that new user's details. Tries to log in, well, it's not going to work because it doesn't find it. So it tells user, oh, I don't know what you're doing, that's not correct credentials. So,
wow, that's supposed to be red.
So we have a way to solve this with stronger consistency guarantees. And how do we do it?
Well, so we've got this thing. It's really something kind of really simple, but we've introduced something called a bookmark. And what do we mean by bookmark? Well, it's a thing that acts as a session token. So it's you can it represents the state of the graph that the user last saw, basically. I'll show how we use it, but practically it's implemented as a string, and that's so that it's portable across lots of languages. You can pass it around. You can potentially pass it all the way back to the user's browser or to a device. It's a small token that we pass around, and we aim it to be opaque. So at the moment, it's basically like a version of the graph. It's effectively like a transaction ID. But in the future, we want to add other capabilities in there, so the routing layer can use it more intelligently in the future. But the same mechanism will apply. So the idea is that you use this mechanism now, and in the end, it gets more powerful. With something like this, we can do something really powerful in the overall architecture. Because if we go back to the same, we try again, the same situation that Max just went through, with the same diagram, but this time, once we do this create the user, when we come back from the database, we're going to get this little red, should be red, little bookmark thing, and it's going to come back out. We extract it out of the database, and we send it all the way back to the end user, the ultimate user's device. And we can keep it around. It's this little string. We can keep it around in the server. So when you make any future request, in order to represent what your user has seen, you forward this token back, and it means that when we get into you see some replication is going on in the meantime. When we finally make a read request on the server, it still hasn't got the transaction. What we do? It's probably like a millisecond until it comes, so we just wait a bit. but we only wait if it's not there yet. So it's not like the preemptive, like waits forever. It's like, or wait in all situations. It's only waiting if I don't have that situation, if I don't have that specific thing that I need. Probably it's going to revive if I do have to wait, it's probably going to revive very, very soon. In which case, I can return back to the user knowing that its time has gone forward. Basically, time is the same or forward of what the user last saw. We have you can set a timeout so that if you have a tolerance on this, you probably will end up going to a different server and you actually find the one that's got the thing that you need. But in the common case, the time of a user interaction is actually way slower than the replication delay. So in general, this makes no difference at all. It's not waiting, but it gives you the safety that if something does go wrong, you're not going to see an old stale state. That's the plan. So how do you do it? Same code again. When we were doing the write transaction, and the important bit here is this yellow last bookmark. It's an addition to the API. And this allows me to just ask the database, hey, you've just done something. How much of the graph have you seen? This is a write query. It could even be a read query. So I've read some stuff. I'm going to display something on the screen to user. I don't want time to go backwards. So tell me how far you've got, what you've just seen. Similarly, when I do a read, I want to say at least, this is where it fits in the diagram. When I would do a read, I want to be able to use that bookmark, and this is where it goes. It's the API has been extended when you begin a transaction to say, hey, this transaction is in a causal consistency chain with associated with this bookmark. So move forward at least as far as this before you begin doing operations inside this transaction. So that's what'll happen here. Just pass it in the begin transaction. And this is kind of showing the part of the diagram where we're actually using the bookmark. So that's our overall architecture. We covered the core, and the core is for updating the graph. The edge is for those queries, the analysis, and the reporting. And we showed the load balancing stuff on top of this. Right. As Emil said, 3.1 beta is available today. So you can actually go and download it from the website, I believe. I hope that's working. And we've got some docs that explain how all this stuff works, how to set up the clusters, and also how to use the drivers in this area. And so the driver stuff, how to write an application, is covered in the developer manual. Setting up the cluster is, we have that in the operations manual. Both of those are published as well to accompany this. And we expect this to go, right now it's only the Java driver that you can use for the load balancing, but the other ones will come by the time we go to GA. I think so thank you very much, everyone. I was going to do some questions. I think we're going to get kicked out.
Thank you very much, Alistair.
We will be just outside and come and grab us straight afterwards. But thank you very much.